Good morning. My name is Mabud Choudhury. First, thank you for attending this session. I thought I'd start with OFS's origin story in terms of where we started. And so OFS is actually one of the oldest and most respected fiber, cable, and optical component company in the world. The OFS entity was actually created in 2001 when Furukawa acquired Lucent Technologies and Bell Labs fiber business unit. And actually between 2001 and 2004, CommScope had a minority stake in OFS, so we've been friends for a long time. There's a lot of history and a lot of close cooperation there. So again, on the superhero theme, we might be the ones with the masks. I never did understand why Clark Kent could put on glasses and disappear. I never quite got that part. But we're not necessarily always visible as a name in the data center space, but our fiber, our cable, and our electronic components are used in solutions with partners such as both CommScope and Finisar. So I'll be talking about a couple of fiber and cable innovations that enables higher speed and higher density in data centers. And as all the previous speakers have said, you can never have enough higher speeds or higher density in a data center, as all of you well know. So I'm going to start, the first topic is for shorter reaches. So these are reaches less than 200 meters of multi-mode cable, or reaches less than 200 meters essentially. And that's been dominated historically by laser-optimized multi-mode fiber, cable, and VCSEL-based transceivers. Christian covered the whole range of transceivers that leading companies like Finisar provide. So we certainly support both single-mode and multi-mode solutions. But there's been this sort of historic benefit for multi-mode and VCSELs that's endured as the data rates have gone up. And one of the core bases for that is that multi-mode has a 50-micron core, while single mode has an 8-micron core. So from an alignment and tolerance perspective, it leads to better, easier coupling to multi-mode, both from the optoelectronics in the transceiver and also in terms of the optical connector. It also means that the multi-mode connectors, because of that larger core, are more resilient to fiber. I think everybody in this room knows it's always inspect, clean, and then connect, and then inspect and clean again. So, but still, that benefit of that sort of resiliency has some advantages in data centers. From a VCSEL perspective, the drive currents are about a factor of 10 lower than in single-mode lasers, and the onboard testing, in a manufacturing perspective, is more cost-effective for multi-mode solutions. So again, these advantages have endured even as the data rates have continued to go up. So I'll do a quick paraphrasing of that Mark Twain quote, that the death of VCSELs and multi-mode has been greatly exaggerated. And every time we talk about the cycle, there's always more life in that technology. And again, companies like Finisar have been leaders in that space for a long time. IEEE, and again, Jason and Christian covered these, have been standardizing, have actually already standardized 50, 100, and 200. So 50 GSR, 100 GSR2, and 200 GSR4 in 802.3 CD. And several of us are involved in the CM standard, 802.3 CM, which is standardizing the 400 gig standards. And again, Jason and Christian touched on both of those. And we're excited that there's a new project. We're actually literally 2 weeks and 1 day away from requesting a new standard in IEEE. The way IEEE 802.3 works is that you do what's called a call for interest to propose a problem that's worth studying. So a study group is formed, and that typically leads to, depending on how fast things go, a 2 or 3 year project to standardize that, that particular PMD or PHY. Again, some of this was covered before. Jason in particular covered the 400 gig SR8 in greater detail. So picking up on SR 4.2, and again, some of what Christian covered, the key here is that it's 50 gigs, it's relying on 50 gig pixels, but it's two wavelengths. So it's a wavelength at 850 and 910. And even though there's been MSAs and proprietary solutions that have used multiple wavelengths, both BiDi and SWDM4, for multimode, this is the first Ethernet standard that's employing two wavelengths. It's based on, as was indicated, an MPO12 connector. It's based on a quad type paradigm, so it's not octal, similar to SR8. So 4-pair cabling, 8 fibers. So it's a seamless migration from 40G SR4 to 100G SR4 to 200G SR4 to now 400G SR4. So especially in enterprise type situations, your cabling plant has extended life from that perspective. In terms of its application use, you can use it for breakout. So right now, IEEE does not have 100 gig SR specified, and we'll talk about that a little bit more in the slides that I have. But you can break out to 100 gig BiDi with this solution for switch-to-server applications. It can be used with all 4 pairs to go SR 4.2 to SR 4.2 in terms of 400 gig applications. And you can do essentially a fiber shuffle where, as Christian indicated, we have switches now with 32 ports of 400 gig, and that could be deployed as a 128-port 100 gig solution in terms of what's available. The reaches are 70 meters in OM3 and 100 meters for OM4. The other key reach that's part of SR 4.2 is OM5. So OM5 goes an additional 50 meters than OM4, so 150 meter reaches is possible because of OM5. And OM5 has gone through the full cycle, and again, this has been a lot of work from OFS, CommScope, Finisar, a lot of other industry leaders in getting it standardized. So both from a component perspective, that's in TIA, and in IEC, it's standardized. From a cabling standard perspective, in ANSI TIA and ISO IEC, it's standardized. And from an application perspective, IEEE has it, and Fiber Channel is the other application that recognizes OM5. So the key here is that OM5 is specified not just at 850, it matches OM4 performance at 850, but it also has a specification at 953. The chart on the right is the EMP guidance from IEC, and it matches what TIA has done, so they're actually in line, where essentially you have greater bandwidth in those wavelengths between 850 and 953, and specifically that means 910 for BiDi solutions, and when you go to 940 for SWDM4 solutions, you can essentially get better reaches and better performance. So I already mentioned, and several of the other speakers have mentioned, that we've got this new project going. So as things are moving from 50 gig lanes to 100 gig lanes, and as was indicated, there's already a IEEE standard for the electrical specification at 100 gig lanes that's been actually under, that project is almost a couple of years at this point in terms of the work there. It's very challenging work, involves a lot of experts in the industry as you're pushing to 100 gig lanes. The chart, the 650 chart that's on the top right there in yellow shows, I think, a chart that Jason had also indicated, that the SerDes rates are moving to 100 gig lanes over the next few years. And so again, if you start the standard today, you expect to have the standard available in the time frame when that transition happens. Switches are going to higher radix, and from a power perspective, I know this question's been asked, James covered that very well in terms of how do you manage that power. So there's, from a server perspective and an accelerator perspective, the power density keeps going up, so there are actually, the trend, especially in hyperscales, is fewer servers or accelerators per rack. So what was traditionally handled with a top-of-rack switch, and your servers and switches all being contained within that rack and within that reach, is now being spread out over multiple racks or of the row. So things going from more of a top of row to a middle of row or end of row type architecture. There's, within the slide, there's Facebook Zion, and that might be in this area, given all the hyperscale data centers here. And Jason touched on AI, basically, and I'll quickly mention that, as Jason indicated, AI started in 1950 or thereabouts. So general AI, which is essentially what babies and toddlers do, turns out there really hasn't been a lot of progress. They do that in a remarkable way, where essentially you don't know the rules, and you just sort of figure it out. And the other thing I would say is that by the time they're teenagers, they go through another reboot, and we're not sure what kind of intelligence that is, as all parents know. So what's happening in these environments is that almost every year, that from a compute, bandwidth, and storage perspective, it's a factor of 10 increase. And again, Jason alluded to this, we're all used to these AI devices, and what was almost literally science fiction 5 or 10 years ago, we've become quickly like, well, this is not good enough, I need another generation of these things. And so, in the same way as with servers, what you're getting is that things can't be contained within the rack. They're moving outside the rack, which again requires more of a middle of row or end of row type solution with 100 gig links. The DACs and CU have a 2-meter objective, and if you listen to a lot of the experts in that area, even that 2 meters might become very challenging, that anything beyond a 1 meter type reach is very difficult with a passive direct attach copper solution. And Jason already covered sort of the challenges of the AOC being more of a point-to-point solution as opposed to a structured cabling solution with pluggable transceivers. I'm actually now going to switch, oops. Okay, I think all right, this might be slightly out of sequence, so I'm switching gears in terms of what we have in terms of going from hundreds of meters of multi-mode cable to dealing with single-mode cable. And so probably one of the biggest advances in high-density cabling is the advent of a concept that OFS refers to as rollable ribbon. So ribbon cables have been very popular for years because you can essentially splice 12 or more fibers simultaneously. The problem is that ribbon cables end up being rigid and they're difficult. They have a preferential plane of bending, so they're difficult to handle. And it's sort of the proverbial putting a square peg in a round hole, or in this case, array of fibers in a cylindrical geometry of a cable. So what happens with rollable ribbon is the fibers, instead of being bonded across the entire length of the fiber array, they're only bonded in certain points. And so they naturally roll up into a circular shape or cylindrical shape during cable manufacture. But with basically finger pressure, they spread out to become an array of connectors that you can splice to with mass fusion. When I mentioned sort of our origin story, part of it was that we're part of Furukawa. And actually, rollable ribbon started now decades ago from an NTT request. So we're leveraging a lot of that knowledge. It's been well established in that market. It's come into the North American market and is being widely deployed now. In terms of its initial application was more for the hyperscale data centers and connecting in a campus type environment, outside plant type applications. But from an OFS perspective and CommScope perspective, we're deploying rollable ribbon technology across all of our cable types because we really see tremendous benefit here. It's 2 times the fiber in the same outside diameter cable, and it's 30% less weight for the same fiber count. And again, this notion of sort of the best of both worlds of a ribbon cable as well as a traditional round cable. So the slide here shows the range of products that we already supply from an OFS perspective, so both for indoor applications, so whether it's riser-rated cables or plenum-rated cables, and also the outside plant cables. Again, the key takeaway here is that the number of fibers per cable is going up dramatically. So one specific example there is that 3456 fiber will fit into a 2-inch duct. So again, that's a huge advantage over existing solutions that are there. I'll quickly mention that a challenge here is that there aren't really standards that govern this technology, so interoperability can be a challenge. So I think being close to your superhero partners at CommScope and other partners becomes crucial in terms of how this is deployed. The other area is, if you want to maximize sort of the density the most, is to go from 250 micron fiber to a 200 micron fiber. Now the glass itself, the cladding diameter stays at 125, the core stays exactly the same. So this is just reducing the coating from 250, which has been traditionally the way single mode fiber has been made, down to 200. It's actually been deployed fairly widely in Europe for almost 10 years, so it's not brand new from that perspective. But since most installed fibers are 250, that transition between those two can be challenging. And again, talk to your trusted partners and superheroes at the CommScope and elsewhere in how to manage that transition. So this is actually, I thought this was the slide that was going to be next, but the other area that we look at essentially is in terms of trunk cables in data centers. The highest density, how do you get that? And so one of the key requirements there is bend-insensitivity. And so how well can you bend those fibers? And the way bending loss is specified in single mode fiber is based on loop diameter. So if you look at ITU's G652D, sort of the generic single mode fiber, it's a 60 millimeter diameter, 30 millimeter radius in terms of that loop diameter. OFS and Corning have a G652D that's actually at 30 meters. So it meets all the optical specifications of G652, but it's a much more bend-insensitive fiber, which enables a higher density solution. Starting in about 2006, because of fiber to the home and some of the PON applications, ITU developed the G657 series of standards, which keeps basically giving, again, these smaller and smaller diameter cables that basically allow for more bend-insensitive products. So, and in terms of OFS has a easy bend fiber for indoor applications that actually is all the way down to 5 millimeters. That doesn't really have the optical loss or PMD performance that you'd need for a data center. So it tends to be A1 and A2 that is typically used in data center high density applications. And just finally, in terms of reinforcing the rollable ribbon story in a data center application, this slide looks at basically for an 8-inch by 12-inch ladder rack, how many fibers you can fit into that space. So on the right side, what you're looking at is essentially a traditional flat ribbon and also a tight buffer with 72 fibers. So if you look at essentially this chart here, what you can see is that you can get about 10,800, well, exactly 10,800 fibers with a tight buffer, and you can get to about 48,000 fibers with the flat ribbon structure. But if you go all the way to the left with a rollable ribbon in 6.2 millimeters, you can accommodate essentially double that, more than double that, 112,000 fibers. And in the middle, what you have is basically a structure where you can get 1728 fibers in a rollable ribbon in a loose tube structure, which basically allows you to get to 165,000 fibers in that same space.